All right, hi everybody. In this video, we are going to work through the process of taking a 3x3 matrix A and first identifying whether that matrix is diagonalizable, and then secondly, constructing a matrix P, which is going to allow us to diagonalize matrix A. So in this case, A is a 3x3 matrix where the first column is 2, 1, minus 1, and the second column is 0, 2, 0, and the third column is 0, 1, 1. So the diagonalization theorem tells us that A is going to be diagonalizable if we can identify 3 linearly independent eigenvectors. And so before we can find eigenvectors, we need to identify what are the eigenvalues. So the first step in diagonalizing a matrix is to find the eigenvalues of that matrix. And one nice way of finding the eigenvalues is to solve the resulting characteristic equation we get when we solve the determinant of A minus lambda, the identity matrix, gives us the 0 vector. So let's first find the eigenvalues for this example. So that means we're going to calculate the determinant of A minus lambda I. So we subtract lambda from each of the diagonal entries, and all of the entries off of the main diagonal don't otherwise get affected. And now we've got a 3x3 matrix, and so let's be strategic about how we're going to calculate the determinant of this matrix. Let's do, for example, a cofactor expansion down the second column. And the reason why is this column has 2 0 entries. So that means we only need to worry about this 2 minus lambda, and then we can cross out the second column and the second row and calculate the determinant of that resulting sub-matrix. And you can verify that the determinant of this matrix is going to give us 2 minus lambda squared times 1 minus lambda. So we see that we have kind of one factor which has multiplicity 2, and we have a second factor that has multiplicity 1. So this tells us we have 2 different eigenvalues. Lambda equals 2 has multiplicity 2, and lambda equals 1 has multiplicity 1. So now that we've identified the 2 eigenvalues, let's try and find eigenvectors and then see whether we have enough eigenvectors to diagonalize this matrix. Okay, so let's continue on to step 2, which is now let's try and determine whether we have 3 linearly independent eigenvectors. And the way that we can identify eigenvectors for a given eigenvalue is we solve the equation A minus lambda I times x equals the 0 vector. So we're going to do this separately for each eigenvalue. We have 2 of them. And then if we have enough eigenvectors, we can construct the matrix P from these eigenvectors and then identify what the corresponding matrix, the diagonal matrix D, is going to be, which is similar to the matrix A that we started with. So let's start by finding eigenvectors for the eigenvalue lambda equals 1, which had multiplicity 1. So we're going to solve this matrix equation A minus lambda I. So in this case, our lambda is 1. So A minus lambda I is going to be the matrix that we get when we subtract the eigenvalue 1 from the diagonal entries and don't do anything to the off-diagonal entries. So subtracting 1 times the identity matrix from A gives us the matrix 1, 1, minus 1 in the first column, 0, 1, 0 in the second column, and then 0, 1, 0 in the third column. So now we would like to identify when, for what vectors x does this solves this equation. And hopefully you can identify that we are going to have non-trivial solutions here because we have a free variable. I can see that row 1 is exactly the same as row 3, for example, just differs by a sign. So we can solve this equation by taking this matrix, writing in its reduced row echelon form, and there's only just a couple of row operations we would need to do. And from this matrix, the matrix of coefficients, we can see that the solution to the homogeneous equation would be x1 has to equal 0, x2 is equal to minus x3, and x3 is free. There's no pivot in column 3, so x3 is free. So we can express that solution set as the set of all vectors of the form x3 times 0, minus 1, 1. So in other words, this vector 0, minus 1, 1, it forms a basis for the eigenspace corresponding to the eigenvalue lambda is equal to 1. All of the eigenvectors corresponding to lambda equals 1 are going to be some scalar multiple of the vector 0, minus 1, 1. So now I have one eigenvector that I'm considering so far. And let's see if we have two other linearly independent eigenvectors from the one that we've just identified by looking at the eigenspace for lambda equals 2 in much the same way that we just did the analysis for lambda equals 1. So we set up the matrix equation A minus lambda I, where now our lambda is 2. So we subtract 2 from the diagonal entries, and we leave the off-diagonal entries alone. And the resulting matrix is now going to be a 3 by 3 matrix, which is 0, 1, minus 1, 0, 0, 0, and then 0, 1, minus 1 as the third column. So I want to solve when does this 3 by 3 matrix times some vector x give me the 0 vector back. And because lambda equals 2 is an eigenvalue, there has to be some non-trivial eigenvector x that satisfies this equation. And solving this homogeneous matrix equation, we can identify the reduced row echelon form of this coefficient matrix has two free variables. There's no pivot in column 2 and there's no pivot in column 3. So the row equivalent reduced row echelon form of this matrix has first column 1, 0, 0. That's our pivot column. The second column is all zeros, 0, 0, 0. And the third column is 1, 0, 0. So from this reduced row echelon form of the coefficient matrix, we can see that x1 plus x3 should equal 0. So in other words, x1 equals minus x3. There's no pivot in column 2, so x2 is free. There's no pivot in column 3, so x3 is free. So we have two free variables. And this gives us a solution set to this homogeneous equation that for any x, which equals x2 times the vector 0, 1, 0, plus some scalar x3 times the vector minus 1, 0, 1. This is going to determine the eigenspace for the eigenvalue lambda equals 2. And so considering this solution set, now we have a basis for the eigenspace for the eigenvalue lambda equals 2. Namely, a basis for this eigenspace is spanned by two vectors, the vector 0, 1, 0 and the vector minus 1, 0, 1 would do the trick. So here we've got a basis for the eigenspace of lambda equals 2. And notice these two vectors in this eigenspace are linearly independent from the first vector that we already found for lambda equals 1. So now we've got 1, 2, 3 linearly independent eigenvectors for matrix A. So that tells me matrix A is diagonalizable. And this matrix P I can construct by taking the first eigenvector I found and making that the first column, taking the second eigenvector that I found and making that the second column, and then the third eigenvector becomes the third and final column to this matrix P. And the ordering that you slot in these vectors doesn't really matter. It's just going to affect the ordering of the diagonal entries on our matrix D that we get in the end. So that's one point to make. A second point to make is I could have identified as a basis for this eigenspace for lambda equals 1, for example, I could have chosen the vector 0, minus 2, 2 instead of 0, minus 1, 1. And I could have used that over here as my first column instead. And this is also fine for such a matrix P. So this matrix P that we identify is not unique. But once I choose a matrix P, then the resulting diagonal matrix that we get is unique. So by choosing the ordering of these vectors in each of the columns of matrix P tells me that the first entry on the diagonal is going to correspond to the eigenvalue of column 1, which was 1. And then the second entry is going to correspond to the eigenvalue of the second column, which was 2. And then the eigenvalue of the third column is again 2. So here we've identified the matrix P that's going to result in giving us a similar diagonal matrix D over here. And so to summarize the process and the result from the previous example, if we want to diagonalize n by n matrix A, first we need to find the eigenvalues of matrix A by setting up the characteristic equation. Then we find eigenvectors for each eigenvalue by solving the matrix equation A minus lambda Ix equals the 0 vector. And if we have enough linearly independent eigenvectors, then we can construct matrix P from those eigenvectors and identify what the resulting diagonal matrix D is going to be. And then it never hurts to verify your results in the end by checking, does the matrix A times P equal the matrix P times D? And so here I've checked those conditions below. Or you can also check whether P inverse times A times P results in matrix D. So that checks out in this case.